Okie dokie. We're just going to dive right into it. This was a short video here that I promised to do 3 slightly more complicated examples of eigenvalues and eigenvector problems, with respect to differential equations, where the eigenvectors weren't the axes. Okay, so let's go ahead and we'll do the first example here with x prime equals x plus y. And y prime equals 1/2 x plus y. Take a moment and figure out what the coefficient matrix is. Okay, it shouldn't be too hard. We got 1, 1. Those are the coefficients for the x and y respectively. The 1/2 and 1 in front of the x and y respectively on the y prime equation. Okay. So now to find eigenvalues, what we're going to be doing is we're going to be taking the determinant of a minus lambda I. So I have 1 minus lambda, 1, 1/2, 1 minus lambda, and I'm setting this determinant equal to 0. All right, this leaves me, that's supposed to be a lambda, not a 1/2, silly goose, minus lambda. Okay, so this leaves me with the polynomial 1 minus lambda squared minus 1/2, and that should be set equal to 0. Okay, doing out the wee bits of algebra we've got lambda squared minus 2 lambda plus 1/2 equals 0, which implies that lambda equals 2 plus or minus the square root of 4 minus 2 all over 2. And so what we've got here is we've got 1 plus or minus root 2 over 2. Okay, now what's important to notice here is root 2 over 2 is smaller than the number 1, so both of these are positive. Okay, so both positive. And what should tell us already from understanding all this stuff is that means we have a repeller because it's pushing in both directions. And I said the magic word, we need to know what directions we are pushing in, because they are obviously not pushing at the same amount. One of them, 1 plus the square root of 2 over 2, is bigger than the other, 1 minus the square root of 2 over 2. Okay, so our task is going to be to find the eigenvectors. Okay, so the first thing I'm going to do here is we're going to take the case of 1 plus the square root of 2 over 2. All right, that's what we're going to be handling with first and foremost. We relook at the equation. Whoops, that's wrong. So a minus lambda, b, c, d minus lambda, and we're going to multiply that by v1, v2, and set that equal to the 0 vector. That's the equation that we're going to be pumping all this into. Doing the arithmetic here, or the accounting, but not showing all my work, I get negative square root of 2 over 2, 1, 1/2, and negative square root of 2 over 2. That times v1, v2 should equal 0, 0. All right. The easiest one to pick is actually the second one, but so to kind of show that here, let's go ahead and let's do that. Okay, 1/2 v1 minus the square root of 2 over 2 v2 should equal the number 0. Okay, now we have a redundant bit of information here. So what can we do to make this the easiest thing possible for us? Well, I'm going to let v1 equal 2. And what that's going to do is it's going to get rid of this fraction right there. Okay, so v1 equals 2. I've got 1 minus root 2 over 2 v2 equals 0. And the reason why that makes this easiest is I've got 1 equals root 2 over 2 v2, which means that v2 ultimately equals root 2. And so I have the eigenvector 2 root 2. Remember, any multiple of this is also a correct answer. Okay, let's go ahead and do the second one real quick. So if lambda 2 equals, what is it, 1 minus root 2 over 2. Then we plug that into our matrix a minus lambda I. We get root 2 over 2, 1, 1/2, and root 2 over 2. Multiply that by an unknown eigenvector, and that should be equivalent to the 0 vector. Okay, again, grabbing the second equation will be the easiest. The reason why the second equation is quote unquote easier than the first equation is because both of these guys have the same denominator, or one of the denominators divides in the other nicely. If I just put the 1 there, then I'm going to have to be clever about my pick in a different way. So again, for this one right here, I'm going to let V1 equal 2, which means V2 equals negative root 2. So we see the sign difference here, okay? So I've got 2 negative root 2. This is not a constant multiple of 2 root 2, which was our other eigenvector. So we are good. We're happy about that. That's good stuff. Okay. So now to put this information onto an axis. Okay. So we've got my y-axis right there. I was starting off so strong with a straight line, and then it just went to pot. And there's my x-axis right there. Okay. Now the first one I'm going to take a look at is lambda 1. Okay, lambda 1 information. It's 1 plus root 2 over 2 and the vector 2 root 2. I'm going to go 1, 2, and root 2 is just a bit over 1. So I'm pointing here-ish. There's my vector. Now, that is for lambda 1. Let's go ahead and color code this because that'll be fun. Okay, lambda 2 is 1 minus root 2 over 2, and it has the eigenvector 2 negative square root of 2. Okay, so I'm going to draw that. So again, over 2 and then down by just as much. Whoops, hit a coffee cup on my desk. So there is that vector right there. Okay, so we've drawn the two vectors. Presumably they cross at the origin, even though I'm craptacular at drawing on my iPad. That's not right either. Jeez Louise. Now we know in the general solution, both of these bad boys are scaled. So if we remember general solution time, x1 is c1 v1 e to the lambda 1t. Okay, so let's go ahead and scale this bad boy, the black one, by any constant. So we're going to get this line right here. This is my straight line solution. Okay, and in a similar fashion, we've got my straight line solution right here for lambda 2. And now of note is, well, what's happening on my straight line solutions? Both lambda 1 and lambda 2 are positive, which means I grow away from the origin, right? My variable is not decaying. I don't have extinction, whatever it is that you want to use for your mnemonic. Okay, now the major question is, well, what does it look like, right? I have two options in some sense, and I'm going to pick a nice thin line for this. Okay, it could look like this, or it could look like this. And so the major question is which one? Because that's important in a very real sense. Pretend it was this first one here, okay? This would mean that as time goes on to infinity, both of my variables go to positive infinity for any initial condition in this region. Okay. What this one is telling me is that for any initial condition, my x variable goes to negative infinity and my y variable goes to infinity. Very different outcomes. So I need to know what the heck is the shape, right? And so to do this, we're going to do a sort of back of the envelope calculation. And what that means is something that is not precise, but is correct. Okay. Now, if we look at what I'm doing, I'm taking the ratio of the exponential parts of my straight line solutions. Okay. And what I've done in a very real sense is I'm treating my numerator as the quote y-axis and my denominator as quote my x-axis. Okay. So if I could kind of tilt this a little bit, you know, what I'm really doing is I'm kind of saying, hey, guess what? This is my coordinate system. I've colored them the way that I want them. Okay. And I say as t goes to infinity, what's happening to this? Okay. Well, this ratio right here is equivalent to, if we notice the e to the t's cancel, and I have an e to the root 2 over 2 minus root 2 over 2, right? Yeah, divided by minus root over 2, so it's going to be multiplied by 2. So this is equivalent to e to the root 2t. Okay, now as t goes to infinity, this goes to infinity. So as time goes on, if I'm looking at my rise over my run, it's going to infinity. So it looks like this. The head of my arrow should go straight up and down with respect to the black axis. Okay. As time goes to negative infinity, i.e. as I go to the tail of my arrow, this thing goes to 0, which means my rise over run is going to go to 0, and so I should look like this at the tail. So I should have a shape like that. And so what that tells me is out here, this is the shape that wins. Okay. In case you are at home watching with a far smaller resolution than that line will allow, this is the shape of trajectories. They're concave in this manner, whatever that means. Okay? Cool. Let's do another example, and what I'm going to do here is I'm just going to kind of skip ahead quite a bit, okay? Let's say, so here's example number 2. Whoa, that is a big chunky pan. I think I want that one. All right, and we're going to say we have the vector y prime is equivalent to -2, -3, -1. That's a lie. And there's the -3. So I have -2, -2, -1, -3. Okay, now to just sort of skip ahead, and I'm going to do it in a different way, and I think it's important to try different ways out. I'm going to compute the trace, which is -5, and the determinant, which is -2 times -3, which is 6, minus -2 times -1, which is 2. So that's 4. Okay, and so my eigenvalues equal trace plus or minus the square root of trace squared minus 4 determinant all over 2. And what this ends up meaning is I have a -1 and a -4. So they're both negative, which means I have decay. So all trajectories are going to be pointing at the origin. Okay. Now, like I said, I'm going to skip ahead a little bit. Lambda 1 equals -1. It has the eigenvector, and you should calculate this at home and make sure this is what you get, 2, -1. And lambda 2 is -4, and it's paired with the eigenvector 1, 1. Okay, cool. So my general solution is comprised of 2 components here. Okay, x is equivalent. Oh, second, I think I'm going to sneeze. No, I'm not. Okay, I didn't mean to write x. I meant to write y1. Okay. y1 is equivalent to c1, the first eigenvector, 2, -1, e to the -t. And my second solution here, my straight line solution, is c2 times the other eigenvector, 1, 1, e to the -4t. Let's draw some axes here. Oh, Lord. I think there's a shortcut. That's not how you draw a straight line. Nope. I thought there was. Just drew a line with my finger. Okay. Draw a straight line there. That's beautiful. And we'll draw another straight line here. That's beautiful. Okay. So this is my first component, and this is my second component of that vector. Okay, great. Now, go through the usual steps. Let's plot 2, 1. Let's go ahead and color code these bad boys. Okay. This one's going to be green. And the other one, to avoid red-green colorblind, is going to be blue. Hopefully you can see the difference between those two. All right, so on the green one, I'm going to draw 2, -1. So 1, 2, -1. So I have an eigenvector that goes to there. Okay, great. And the other one is 1, 1. So that eigenvector just looks like that right there. Okay, fantastic. Now, we have these coefficients in front. I'm going to use that as motivation for just extending those lines all the way out as far as they can go, writing over those equations that I wrote so carefully for us. Those are my straight line solutions. I promise you, those are straight lines. Okay. Now, associated with each of them is a negative eigenvalue. So along both of these, I am crashing in toward the origin. Now, if we're clever, we should be able to say, hey, along the green, I am decaying slower than along the blue, because that e to the minus t decays slower than e to the negative 4t. Let's make that a bit more precise, okay? So I'm going to treat my blue as my vertical axis. I always try to pick the one that's like just an easy flip rotation. I don't know why. Rotating this way doesn't make a whole lot of sense to me in my brain parts. I have weird brain parts. So I have e to the minus 4t, whoops, divided by e to the minus t. This is incredibly thick. E to the minus 3t. Okay, so what I'm doing here is I'm considering, whoops, an axis, a coordinate system like this. Okay, and for those of you who take linear algebra, you know, we've got a two-dimensional set of vectors here. We've got a basis. So like really there's a transformation that can take us from the XY axis to this blue-green axis. And in fact, we know what the transformation is. It's kind of up there. But anyway, we have e to the negative 3t, which means as time goes to infinity, this goes to 0. So in a very real sense, over here, I'm flat in accordance to my blue-green axis at the head of my arrows. My head of my arrows goes to the origin. So I'm flat in this sense. Whoop. And as time goes to negative infinity, this blows up, which means the tail of my trajectory is going to be straight up and down. So I'm going to look like this. So I look like that. I hope that makes sense to you guys. Okay. So over here, if I want to plot out some trajectories, and since we're doing sketches, like the only things you got to make sure is that when you draw two orange lines, they don't cross, that they observe this concavity restriction that we've constructed with our back of the envelope calculations here. And voila, you've got your sink right there, your nodal sink. All right, one last one to end this short video. Okay, on this last example here, whoop, example. I'm not even going to give you the system, but what you should do is you should take it as a challenge to try to construct what is the system that gives us this. So lambda 1 is 2, and that goes with the eigenvector 11, 6. And lambda 2 is negative 3, and that goes with the eigenvector, I almost said 0, 0, 1, 1. All right. We're going to make a small change to my paper here because I have a much larger number. Okay, so we're going to have a tighter grid. So let's go ahead and make my two axes here, my second component and my first component to whatever the vector is that we've decided to describe our system with. Okay, now to do color coding again, let's use purple just to change things up a little bit. All right, purple is going to be lambda 1. Okay, now what that means is that my first solution looks like C1, 11, 6, e to the 2t. So let's find 11, 6 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. Oh, I almost had it perfect by accident. Trying to draw a straight line, a straight line, a straight line. Oh, I did a good job. Okay, great. So that's my straight line solution right there for that. And my eigenvalue is positive, which means I'm growing away from the origin. All right. The second solution, let's pick a color we've never used before, brown. I've never used the brown. This is exciting. All right. Now, this gives me my second solution of C2, 1, 1, e to the minus 3t. I've never used brown before, and then I proceed to just draw a garbage formula, e to the minus 3t. Okay, great. So I'm going to find 1, 1, which is right there in the corner. And I'm going to sketch that straight line solution. I'm trying to be very precise because I can be. And it would be funner if it looked pretty. Okay, there we go. Now this is associated with a negative eigenvalue, which means along this straight line solution, I'm crashing in toward the origin. Comme ça. All right. Now, this one you don't really need to do as much of a back of the envelope calculation to figure out what goes on for particular initial conditions. All right. Let's pick a initial condition up here in the first quadrant above the brown curve, just above the brown curve. Bloop. Right there. Okay. So right now, if I look at it, which solution am I closest to? I'm closest to the brown solution. So I should look the most like the brown solution. All right. And I'm going to travel down like it, heading toward, but then, oh, I veer off and I start to look more like the magenta solution. And as I move out, I get more and more kind of curvy like that. Similarly, I get something like this over here, where I just sort of bow away from the origin. In between the brown and the purple eigenvectors in the first quadrant, I go down and then back up. I have some sort of slope. Now I'm going to pick a much skinnier pen here. So sorry if your resolution doesn't pick this up. I kind of crashed down to 0, and as long as I've got these loopy loops in here, and as long as my loopy loops don't cross, it's a good enough sketch for me. Right? So we can see here that a saddle doesn't have to look all perfect and symmetric like this. My eigenvectors, my straight line solutions, can be quite skewed to one another, and we can get this squishiness here where we have these gentle trajectories on the outside and then these really sharp turning trajectories on the inside. Okay. Yeah, I guess that's it for the short video. Thank you very much for tuning in. I'm going to make another short video right now once I find the stop recording button.